Welcome, everyone. Today's talk in this TSU-Georgia Smart online course series is given by Professor Koki Ho. Professor Ho is assistant professor at the Department of Aerospace Engineering of Georgia Tech. I will tell you later on what his title is in case you have not seen it. But I want to tell you that he got his bachelor degree and master degree from University of Tokyo, and then he got his PhD from MIT. He had a very, I would say, outstanding career as a young scientist, and he got a number of awards already, just including 2015 Luigi Napolitano Award. And then in 2019, he got the NASA Early Career Faculty Award and also the DARPA Young Faculty Award. In 2020, he got the NSF Career Award. So he's a well awarded the young professor. He's now visiting Rome, Italy. That's why we are having this seminar at this hour, because it's the morning in Italy. And Professor Ho's special interest is in space mission analysis, design, and optimization. And especially, I'm interested particularly in his research on mega-scale satellite constellation design. That must be very interesting. Anyway, I think he will talk about this, and his title is Space Logistics and Mission Design. Professor Ho, please.
Thank you very much for the introduction, and also thank you for the flexibility to change the time because of the time zone issue. So I'm currently visiting Rome to visit my family, so that's why this time was more helpful for me. So in today's talk, I want to talk about my research area on space logistics and mission design. So originally, when I had the discussion with Dr. Lightsey, we were thinking, what topic to put in. And if we want to align my research with Smart Center, probably we can talk about some of the SmallSat programs which I worked on in the past. But I think all other talks are about SmallSat. So I thought maybe I can talk about something else, something different, about my research on space logistics and mission design, in case some of these become of interest to you. Also add some kind of diversity of the topics to this seminar series. So that's why I chose this topic, space logistics and mission design. I will talk about the different applications, which include mega-scale constellation, and also on-orbit servicing, and a little bit about space mission design for human space exploration as well. So that if any of these topics are of interest to you, please let me know. I'm happy to discuss in more detail offline. So I added a slide to just introduce myself again. So this is kind of repeating a little bit. I'm currently assistant professor at Georgia Tech. My promotion is approved. So from this August, I will be associate professor. And so I'm directing a group called Space Systems Optimization Group. I started my position at Georgia Tech in 2019. Before that, I was at University of Illinois Urbana-Champaign. So because I'm going to talk about space logistics, I can include this title there. I'm actually chairing a technical committee within AWA called AWA Space Logistics Technical Committee. I will talk about what I mean by space logistics in a little bit. And so the photos here, the left one is Illinois, where I was before, and the right one is Georgia Tech. So it's kind of in a very different environment. One is in the kind of college town in the middle of nowhere in a sense, and then Georgia Tech is in the middle of a city. Both of them are nice campuses. If you have a chance to visit them, I think you'll enjoy them. In the meantime, I spent some time at JPL as a visiting researcher, and some time at Airbus Defense and Space, which was known as Astrum back in 2010, where I worked on Bepi Colombo project, which is now on the way to Mercury, which is pretty exciting. Okay, so About my research group currently at Georgia Tech. So what we do is we create, we do research in optimization and modeling. So the mission of our group is to create optimization methods and models to tackle complex space mission design system engineering challenges. So ideally, we're trying to develop some new method based on optimization method to solve some of the problems that cannot be solved by hand, for example, or that some hidden challenge, some new challenges that is caused by driven by the growing complexity of space missions. So especially from logistics perspective, some of the optimization methods and models we develop are driven by the ideas from terrestrial logistics. So on the ground, when we have a lot of logistics companies like FedEx and Amazon, and all these companies have some logistics challenges, and they have there are a lot of research. There's a lot of research that tackle those challenges for terrestrial logistics problems. And the space missions were not as complex as those terrestrial logistics in the past, but the complexity in space missions is definitely growing. And the logistics becomes a challenge over time. So we're trying to see how this terrestrial logistics paradigm can inspire some of the new methods to optimize and model the complex space mission. So that's kind of the high-level statement of a lot of the research I'll be introducing today. So I'll be talking about 3 applications. The first one is space exploration mission design. So this is more from a human exploration perspective. This figure is a little bit old, but it basically shows mission to Mars via Moon. So basically, NASA is trying to put together a vision to go back to the Moon, send human back to the Moon through a program called Artemis. And in the meantime, build a lot of different capabilities in the cislunar space, which is basically the space between Earth and the Moon, and then leverage those capabilities and eventually send human to Mars. So that's kind of some of the kind of vision that NASA, as well as many other international partners, have been having. So what we will address here is to design a campaign. What I mean by campaign is a series of missions that is designed in a coordinated way. So we don't have independent missions so that they don't interact with each other. Instead, we have a series of missions, and each of them will interact with each other, and so that we need to design all these missions in a coordinated way. So that's what I mean by campaign. So I'll talk about some of the research behind those campaign design. The second topic, the middle one, is on-orbit servicing, assembly, manufacturing. This is becoming a kind of hot topic. It's like a buzzword now in the U.S., DoD, Department of Defense especially. So all these satellites get old, and we want to do we want to launch new ones and discard all these old ones, or do we want to provide some servicing or repair or refuel to those existing satellites so that we can basically extend the life of these satellites? So this is kind of ongoing topic that we're highly interested in, and this is, of course, a logistics problem. That's what we do on the ground. That's what, for example, Amazon or other Apple or those logistics branches in those companies do as well. So this is kind of almost a definition of logistics in the space paradigm. And the last one is small sat constellation. So we are seeing a trend of mega scale constellation, like a SpaceX Starlink constellation, or OneWeb, or and Amazon is also having a similar concept. So all these kind of large scale, mega scale constellation with hundreds of thousands of satellites will be different than the old ideas, from previous ideas of constellation. Previous ideas, the biggest we could think of is like Iridium, which has less than 100 satellites. I mean, it's still many compared with what we deal with normally, but it's on the order of tens of satellites. But the mega scale constellation, we're talking about hundreds of thousands. So definitely there are a lot of challenges that is that is caused by this scalability issue. I'll be talking about some of those as well. So these are the three topics I'll be talking about today. But our group is also doing other researching other application areas, as long as they're related to optimization models and methods. So I said I would introduce space logistics a little bit. Like I said, I'm currently chairing this technical committee, and we kind of manage the definition of space logistics, at least from the ARWA perspective. ARWA, by the way, stands for American Institute of Aeronautics and Astronautics. It's an organization that runs the conferences for aerospace area. So space logistics, we defined it as a theory and practice of driving space system design for operability and supportability, and of managing the flow of material, services, and information needed throughout the space system lifecycle. So there are several keywords here. So first of all, we're talking about, of course, we're talking about theory and practice of driving space system design. So this is all about how we design and how we operate the missions. And especially we want to design the mission so that it can operate in a smooth way. So we're designing the system with operation in consideration. And also the supportability or sustainability is becoming an issue, especially when we start to think about servicing or refueling and so on, which again is almost the very definition of logistics in the space paradigm. And a lot of the space logistics is about the traffic management, managing the flow of material, services, and information in space. So I'll be mostly talking about material, commodities, or payloads. But the services and information are, of course, also, especially the information or data, logistics is also an important component to consider when we design space missions. And the last keyword here is designing the mission throughout a space system lifecycle. So we're not considering one mission or one vehicle. We are considering a series of missions over a life cycle of a system. So that is kind of the key element in the space logistics, and what makes it different from a more kind of conventional space mission design that typically focus on one vehicle or one mission. So from here, I want to talk about this first domain, campaign level space exploration mission design. So this is again from the perspective of human space exploration. So when we think about past or current space exploration, like Apollo or International Space Station, like those are kind of missions, representative missions of human space exploration that has happened in the past or ongoing. Apollo used, from a logistics perspective, Apollo used a strategy called carry-along strategy. Basically, what that means is that it carries everything it needs to the destination and comes back. And the next mission is completely independent. You carry new things to the destination and comes back. So from logistics perspective, each mission was independent. ISS, on the other hand, used a strategy called resupply. That basically means that you have a station up there, but you don't carry everything with you in the beginning. You basically will resupply the consumables or replace equipment or even replace a crew. So that is kind of the kind of opposite of what Apollo did from a logistics perspective. Now, but when we think about the future space exploration, we will have multiple destinations like the moon and Mars, like we saw in the first figure, the NASA's vision, and also near Earth objects like asteroid. We had a lot of different discussion about visiting asteroid, maybe even mining the asteroid. And we also have more players joining this enterprise, like not only NASA, not only ESA or JAXA, but we also have a Russian, we'll see, but also the commercial players. More importantly, this is kind of the reason the commercial players is important is because it is kind of a new way to look at this space exploration. When the commercial players like SpaceX or Blue Origin comes in, we'll have a different way to think about space mission, different way to design these missions, especially how to make this commercial sector profitable, so that we have incentives for more and more commercial players to join this enterprise. And so those perspectives will require a different way to again think about how to design missions, which is why I think it's kind of very important to see to consider those factors. Of course, international collaboration itself is already very challenging between the U.S. And Europe, Russia, and Japan. That's already a very challenging problem. But having a commercial players in the loop is a completely different problem, and we need to think about it very carefully, so that the paradigm becomes more sustainable and kind of welcoming in a sense to new players as well, beyond SpaceX and Blue Origin, who kind of already joined the enterprise. And so with those kind of new trend or a different perspective of space exploration, that is different from the Apollo ISS, we need to also think about the logistics paradigm. So maybe the new logistics paradigm can be a combination of pre-positioning, or carry along, or resupply. Or maybe it can be more complex than that, and it can maybe use some of the resource from the environment. By resource, I mean, for example, we can mine some resource from the moon or from Mars, and this is called the in situ resource utilization, or ISRU. So one of the examples that's already demonstrated is to get oxygen from the Mars atmosphere. So Mars atmosphere has a lot of CO2, so we can get oxygen out of that. And the MOXIE experiment on the Mars 2020 Perseverance rover has done the experiment successfully. So we have that technology demonstrated already, at least at a small scale. So oxygen is useful as a propellant. So you can use that as a for rocket. Of course, the amount that's being generated now in the MOXIE is just a small amount. But if you can scale up some of these technologies and use those resource for the rocket propellant, then we don't need to carry all the rocket propellant from the ground, right? So that can really change the way we design the space mission. So it's not just about whether we do carry along or resupply. We have multiple sources now. We can get resource from different sources other than the Earth. And propellant is a large mass fraction for rockets. So if we can save the propellant, then we can save a lot of mass, which eventually can lead to a lot of saving the cost. Now, this ISRU is, again, like an oil field in space. So I used a propellant as an example, but of course, oxygen can be used as a life support gas as well. And if you can get hydrogen as well, then you can get water. Or if you can access water ice on the moon or Mars, and that can also be water. So that can, of course, be used for human life support. So, but this ISRU is not a magic. So in order to use this ISRU, you need to deploy these plans beforehand, which of course require cost. And that plant mass is a pretty large, and you need to wait until it starts to generate the resource. And you need to also think about the maintenance of this ISRU plant. And of course, it's also a challenge about, can it be fully robotic, or you need human to, be there to maintain the ISRU plant and so on. Maybe human doesn't need to be there permanently, but maybe we need the maintenance visits to make sure everything works as planned. Or we need to consider the deteriorating performance of the ISRU over time as part of the mission design. So, and also ISRU typically is on the surface of the moon or Mars. But in order to use this propellant effectively, we don't want to go to the actual mining site on the moon to get those resources every time we need it. We probably need some gas station in orbit, which is called propellant depot, where we can store the propellant, or maybe even some structure like a tank for the propellant in space. And those propellant depot can be at Lagrangian points, which is a kind of stable orbital point in the not necessarily stable, but equilibrium orbital points in the cislunar space. Some of them are stable, others are not. But still, those are kind of one of the ideal options to store some of this propellant. And or we can store those in the Earth orbit, or or in some other orbit between Earth and the Moon or Mars. Now, this propellant depot, again, it's not a magic. Of course, we need another set of infrastructure to refuel this propellant depot regularly using a tanker from the source of the resource, either Earth or ISRU plant. So these tankers need to be managed in an effective way. And also, if we store propellant in the propellant time, then there will be a boil off, which means that you will start to lose the resource over time. So I guess the point here is really that all this technology have pros and cons. And if we want to start to talk about using this technology, which is a very active discussion topic nowadays in the space exploration community, we need to consider both the cost and benefit, right? So considering all the limitation and the cost that's and the launch mass that's needed to make those technologies possible, are they still kind of are they going to pay off? Basically, are they effective or efficient at the campaign level when we consider both the deployment of those infrastructure and the utilization of those infrastructure? So that is kind of a question that have been discussed everywhere. So of course, ISRU engineers or technology experts, they will say, the ISRU is definitely very, very effective, so we should definitely use that. And of course, the opposite side of the discussion will basically say that no, this you need that much to launch them, so it's very expensive. The development cost is not negligible, and so on. So all this qualitative discussion can, of course, happen, for example, in conferences, in other places, in those discussions. But if we can design the whole campaign all at the same time, in a rigorous way, we can answer those questions, of course, under a certain assumption. So if you have a list of assumptions, then you can use mathematical optimization to tell you whether this, what is the best way to use those technologies. So that's basically a kind of long introduction to what I'm going to talk about in this first domain. So our idea is to use to basically get inspiration from the terrestrial logistics. And one of the ideas is to consider the space mission design as a network optimization problem. So we consider this potential orbital node as basically vertex or nodes in the network, and we connect them using arcs or edges. Those arcs correspond to for example, the trajectory between connecting a different set of orbits. For example, this LEO is low Earth orbit, EML1 is Earth-Moon Lagrangian point 1. So this arc basically means that the trajectory that connects the LEO and the EML1. And this is a multi-commodity flow that flow over this network, because every trajectory, if you want to flow some commodity over trajectory, we need to treat the commodities separately. We need to treat the payload, vehicle, propellant, food, water, waste, structure, even crew as a different commodity. And we consider how this commodity will flow over this network. Of course, we have a set of constraints that says, for example, when you have a propellant, you need a certain tank. When you have crew, you need a certain water and food and so on. So all these constraints are considered. Then, and we have some demand, some needs. Say we need to deliver this mass to Mars, to the Moon, and so on. With all this demand and with all these constraints, what is the best way to send to basically satisfy those demands? Best can be defined as lowest cost or lowest launch mass. So that is kind of the optimization problem we're looking at. And we can go a step further. So not just about how we carry stuff or when we launch what, but also design the spacecraft or stages of the spacecraft themselves. because it's in many cases for space missions, we have a spacecraft dedicated for certain type of missions. So it's different from the ground where you have a train designed without considering where the train goes, right? You just design train, and usually that's pretty standardized already. And wherever you go, you can use that train, as long as the interface matches and so on. But in space, it's a little bit different. So, for example, Apollo basically had a dedicated vehicle designed for Apollo missions. Artemis is happening in a similar way. So the spacecraft design is part of the problem in many cases. So so that is kind of another challenge. How do we consider spacecraft design as part of the problem? Which again is a unique challenge in space logistics. This doesn't really happen in the ground logistics. Amazon, for example, doesn't design its own track from scratch. And also another challenge is infrastructure design. So I talked about ISRU, but ISRU, of course, you need to design the whole ISRU system. ISRU is not just again a black box. It has a power system, storage system, excavator, and hopper. So basically, it has a lot of different subsystems behind ISRU that needs to be optimized. And of course, we don't want to have a too small ISRU that doesn't generate enough resource. We don't have a too big ISRU that require a lot of cost to deploy. So there definitely is the optimal size of ISRU, which need to be optimized together with the space mission design and the spacecraft design. And the same for the program depot as well. So basically, we are having a very big problem here, big in terms of multidisciplinary. So we need to consider different multidisciplinary. One is commodity transportation flow for payload, program, consumables, and so on. And the sizing or choice, if we have multiple choices, and choice of spacecraft, as well as the infrastructure used for each leg of the mission. And finally, we need to consider the timeline. We need to consider time horizon when we want to launch what from where to where. So this whole problem needs to be considered all at once in an optimization problem. So this is kind of, I will not get into the detail of this formulation, but this is one of the formulation we have developed. We have a different variation of that depending on the problem we're interested in. So this is a multi-commodity flow, and we consider each pair of nodes and edge connected with them. For example, we consider node I and node J at I at time t and J at t plus delta t ij. This delta t ij is the time of flight from this node I to node J. And of course, if you have multiple trajectory options, then we can have multiple options for this edge or arc. And then we have a commodity that flow over this arc, and we consider X as a vector. So it's a multi-commodity. Therefore, it has a series of vector. Each element of this vector corresponds to, for example, the oxygen or propellant tank or crew or other commodities. And Y is a vehicle. So we consider spacecraft vehicle. And Y is an integer variable that shows how many vehicles you need for the type V. So V is a spacecraft type. So we can consider multiple types of spacecraft. We don't need to use the same spacecraft everywhere in a mission. We can use different types of spacecraft. So V is the index for that, and Y is the integer variable that shows how many spacecraft you need for that type V. So with this variable, so this X and Y are the variables, and we can define the cost. If it's a launch mass, then it's just the cost that goes through the arc from the Earth's surface to the low Earth orbit, or wherever the parking orbit is. If you have other cost function, then you can define it in that way. We have a mass balance constraint, which basically said that whatever that goes into this node I and whatever that comes out of this node I need to be balanced. And the difference should be within the demand or supply that happens at this node I. And we have flow transformation that basically transform this this X plots, which is basically the outflow from node I into the X minus, which is inflow into node J. So this can show, for example, how much propellant has been used during this flight from node I to node J. And flow capacity basically shows the constraints between each of these commodities. Like in order to carry a propellant, you need to have a sufficient size of a tank, for example. And we have a flow non-negativity, basically shows the time horizon. And lastly, we have this spacecraft sizing model, which I just use a very general function here. Normally, the spacecraft sizing model becomes a nonlinear model, but we often can use a piecewise linear function to make it make a whole problem mixed integer linear programming, or we can use a multidisciplinary design optimization approach to consider this nonlinear model as a decoupled subproblem, and we can iteratively solve the problem to reach a solution, which, by the way, has been demonstrated as a very effective way. We just had a journal paper on this topic that was accepted yesterday. So if you're interested in these details, I'm happy to share those papers with you. So from here, I just will skip all the technical details, just talk about the case study, just to show what this can do. So for example, when we consider a prototype, but this time we'll consider a little bit expanded version of Apollo, we send a little bit more crew members and larger payload. And the network in this case is quite simple. You just go to low Earth orbit, you go to low lunar orbit, and you go to lunar surface. And each of them, these arcs have delta V and time of flight defined based on the trajectory model. And we, in this simple case, we just assume those numbers, which was calculated separately. And then we have all these assumptions shown here. The bottom table is basically the input that goes into this model. We just say we have the demand, for example, say at day 5 every year. So let's say this mission repeats it once a year. And for every single mission, we have this at day 5 after launch, we want to have 12 crew member. Negative 12 of supply means a demand of 12 crew members. So we need to deliver 12 crew member to the moon at day 5. At day 8, we have a 12 crew member kind of appears on the moon that were ready to go back to the Earth. And at day 3, at day 13, this crew member will go back to the Earth. So that's kind of the supply and demand, right? And then we have equipment that needs to happen at that needs to be delivered to the moon at day 5, which has this mass 4,200 kilogram. And finally, we can bring some sample back to the Earth from the moon. So let's consider this demand and supply scenario. And from here, we can consider multiple cases. Let's say we just do it once. We just have a single mission. So this is a solution that we obtain. By the way, the only information we gave to the optimizer is the demand and supply. We didn't tell optimizer how to deliver those demand and supply. And this is what the optimizer came up with. Optimizer says, let's use this spacecraft module sizing. So this sizing is obtained by the optimizer. And it says, we have the 2 types of stages, stage 1, stage 2. And we can deliver, we have all these stages departing the Earth. So low Earth orbit, we ignore how we deliver stuff to low Earth orbit, which probably will use some of these rockets available. And after that, we go to the low lunar orbit. And then here it says that let's leave a stage at low lunar orbit, and the rest goes to the moon. This stage that is left at the low lunar orbit is a bigger one. And then, the crew goes to the moon and do whatever they need to do. And then on the way back, it basically leaves these stages, and the crew will, be on this small stage and come back to the low lunar orbit and dock with this large stage, and they will come back only using the small stages after receiving the resource from these large stages. So this is kind of the entire logistics flow that have been found by the optimizer. And this has not been given to the optimizer. We only told the optimizer to send this crew to the destination and back, and send this equipment, bring some sample back. And all this scenario is like, for example, leaving one stage in low lunar orbit. And so all these scenarios were found by the optimizer. So this is, by the way, very similar as Apollo. It's not exactly the same as Apollo because of the difference in the assumptions, and Apollo did not necessarily choose the most optimal way because there are other constraints. But still, Apollo had one vehicle, one stage waiting in the low lunar orbit, and so on. So this is all, all consistent with what Apollo actually did, even though we didn't tell the optimizer to do so. And but this is just for single mission case, which probably is not as complex as it could be, because we can probably come up with it just by hand as well. But when we consider multiple missions, then problem becomes more complex. So this is a 3-mission case. And 3-mission case, you would think that we can just repeat the single mission case 3 times, which of course is an option. But optimizer says that we can probably do better than that. And the optimizer basically chose to send the ISRU, or the mining plan, to the moon. And it will optimize the size of the mining plan. In this case, it's sending 1,454 kilogram of ISRU plant, in addition to the crew and equipment. So you are having a little bit larger vehicle size this time. It's not shown here, but actually the vehicle size is a little bit larger than the previous case. And it's all considered by the optimizer so that every constraint is satisfied. And the ISRU will go to the moon. It will not be useful in the first mission because you need time to generate the resource. But in the second mission, you will start to generate resources, and those resources can be used by the missions, the second and the third mission. So the second mission, as you may notice, we have less stages now. We don't need to have all 4 stages like the first mission had. And then it will consider how much a vehicle or structure you need in the low lunar orbit to store the propellant to be used in the future, and it will consider all this, the design of the vehicle, design of the ISRU, and everything, so that you can achieve the optimal solution after considering all these 3-mission campaign. In the third mission, as you can see, you need even smaller stages. So every time you need smaller and smaller stages because you have the ISRU already launched in the first mission. And this ISRU, launching this ISRU is not free. Again, it requires a cost. Therefore, if you only run one mission or even 2 missions, the optimizer would not say, let's use ISRU. But if you start to use 3 missions or more, then optimizer turns out to choose to use ISRU technologies. So again, this is rigorous. So we're not telling the optimizer to use ISRU or not. We only tell the optimizer what is the supply and demand, what is the technology performance, and so on. And the optimizer will tell you what is the best way to use this technology. So you provide a rigorous way and a non-biased way, in a sense, assuming the model is non-biased, to answer the question whether ISRU is useful or not, and how to optimally use those ISRU technologies. And this optimization problem that's shown here only takes 300 seconds on the desktop computer. So it's really very efficient because of the approximation using piecewise linear models. And so this work was sponsored by NASA and United Launch Alliance. So we did a different version of this work for different purposes. And I think it worked pretty well, and it was well received. So that is the first domain. I know I'm probably a little bit running over time, so I'll go a little bit quick for the second and the third domain because I want to cover all 3 of them. So the goal here is really to provide an effective decision support tool for automated space campaign design analysis without biased discussion, or to basically automate the mission design process as much as we can. So the second domain is autonomous servicing, assembly, manufacturing. So like I mentioned, this is becoming very, maybe recently I think White House changed the word to in-space servicing, assembly, manufacturing. They used to call it OSAM. Now they call it ISAM or ISAM. I don't know how to read it, but so they changed the acronym over time, but basically it's saying the same thing. So we're trying to refuel or repair the satellite after instead of completely retire them and launch a new one, so that we can extend the life of those satellites. And we're mostly talking about geosynchronous orbit, which is very expensive, to launch a satellite to. But some some groups are also looking to the autonomous servicing for LEO satellites. So we developed a different set of ideas to tackle this kind of problem. So one is to use simulations. So simulations basically, so there are different types of simulations, but agent-based simulation is what typically is used. So basically, you try to simulate the stochastic behavior of failures, of random failures, and the random location of the failures, of course, and also the behavior of the service to respond to those failures, and then we can run the numerical simulations over a very long time, many times. Now, of course, that's great, and we have a published paper on that, and that works pretty well. But that's not very useful for optimization because it takes a very long time to evaluate even one strategy. Now, so we're thinking whether we can make this more efficient using some of the semi-analytic model. And so that's where we try to draw some inspiration from the terrestrial logistics. So when we think about how we design a firefighter station, we don't know where the fire is, we don't know when the fire happens, but we can use spatial queuing theory to consider this fire management problem, and that is an analytical method. So why don't we do the same for space autonomous servicing as well? Now the problem is not that simple because now we need to consider orbital mechanics, and we also need to consider the spare that's needed to provide the service. So fire, you basically just need water to extinguish fire, but for repair you probably need some spares. So if you consider, for example, modular satellite, and you have some module that failed and you want to replace that module, which is one of the concepts that we have looked into with DARPA in the past. But then you need to carry a spare module so that it's easy to replace that module, so that you don't need to kind of do more detailed servicing in orbit. So that is kind of one idea. There are other ideas about on-orbit servicing too. To for example, literally cut the wire and do all the repair in orbit. But that's kind of the technology maturation level is a little bit lower if we are talking about more complex operations for on-orbit servicing, fully robotic. So therefore, we need, in either case, we need to consider the spares. So the spares comes down to inventory management problem because these spares need to be launched from the ground. So we can, consider like a firefighting station where you just go everywhere and just fire and extinguish the fire, and that's it. We need to consider the resupplying the spares in the servicer, and maybe even have a like our propellant depot, but a spare depot that store those spares, and we have some logistics vehicle that carry those spares from the ground to that depot, and we have a servicer that use spares in those depot to respond to these failures that happen randomly in, for example, geosynchronous orbit. So that's kind of what we try to do. So we want to modify the existing spatial queuing theory with orbital mechanics considered, although it's in geosynchronous orbit, so it's not it's just a phasing maneuver. It's not a very complex orbital mechanics, but we did consider some other types of orbit as well for other studies, and combine that modified spatial queuing theory with inventory management, considering how we can launch the spares so that we make sure that the probability of satisfying the demand is above some certain requirement. So this becomes almost analytic, but with some iteration. So that's why we call it semi-analytic method. So this basically is one example to show a case study seeing that the analytic method, semi-analytic method we're proposing is replicating the simulation result very well. So this is a trade-off between the depot capacity and the mean waiting time. So mean waiting time basically means that when a failure happens, how long does it take to get the failure repaired or basically serviced? And that's of course one of the metric that we care about. We want to make sure that we provide responsive services. And then there's this x-axis, which is depot capacity. So the bigger the depot, of course, the shorter time you have to wait, because you don't need to wait until the next launch. but you don't want to make the depot capacity too big, because that means that you need a lot of cost to maintain that, like a station keeping costs or other maintenance costs. So there's of course a trade-off between the mean waiting time and the depot capacity. So basically the performance versus cost. And this trade-off, as you can see, will show this kind of curve, and we're interested in the knee point somewhere here. And this blue dashed line is a semi-analytic model we developed, and simulation is a black line. And as you can see, we are replicating the simulation in a very effective way. And it requires significantly less time, like in the order of seconds, where the simulation can take on the order of hours or maybe even longer. So there's a significant reduction in the computation time, which enable us to do a lot of different optimization, because we can just change different design parameters and see how it performs very quickly without running a long simulation. So that's kind of one of the contributions we made in autonomous servicing. And going a step further, we can consider a network like we did for the previous case, for the human space exploration. We can consider a network optimization problem for on-orbit servicing. We can consider it in the rolling horizon perspective, and considering multiple commodity, multiple types of thrusters. So this is not just vehicle routing, but capture the entire logistics flow, including the spares that's needed, and even tools that's needed, and the launch logistics, and of course the servicing logistics of one or multiple vehicles, and the optimal combination of high thrust, low thrust, and all these features are considered in this model. And so this model can be useful for both short-term tactical scheduling or long-term strategic planning. We have demonstrated both cases, and we're planning to publish. I mean, the work itself has been published on journal papers. We're planning to publish those in as an open source tool in this fall. This work has been mostly funded by DARPA, and we are starting a new project by Space Force that looks into how to use this kind of methodology or tool for to work with industry and to actually make it apply to real missions. So the last but not least domain I want to talk about is mega scale constellation. So as you know, there is a recent trend by SpaceX, Amazon, and so on, and of this hundreds or thousands of satellites as a constellation. And I believe that we believe that there are some hidden challenges in this trend of mega constellation. Basically, the lack of scalability of the existing method. And some of the challenges include the deployment, maintenance, logistics. Maintenance here, I mean the spares. So how we allocate the spares so that this constellation can still continue servicing even if some satellites stop working. And debris management. So if we start to retire those satellites, this is a large number of satellites, like hundreds of thousands. How do we retire those satellites in an effective way so that we don't create a large amount of debris in an unnecessary or unfavorable way? So basically, we are trying to tackle some of the scalability challenge of existing method. So one of the idea that I want to talk about that we have worked on in the past is to consider the spare strategy. So how do we make sure, again, that we'll continue the service above certain requirement, like for example, 99.9 time of the time we have a continuous service, assuming this satellite are for communication, like Starlink. So we want to make sure they have uninterrupted service as much as possible with some requirement. But the satellite can fail at any time. So we want to have spare satellite. So how do we make sure that we have enough spare satellite? Now, why can we use same technique as before, like Iridium used? In the past, we didn't have many satellites. We have maybe again on the order of 10 satellites. Then the spare strategy we have used is to have 1 or 2 more spare per orbital plane, and that was sufficient. And each satellite was also has a high reliability, So that was it was a big satellite, not really CubeSat or SmallSat. So we only need 1 or 2 spares per plane. We didn't need to rethink about where to put this. We just you know, have a little bit more redundancy. That was it. That was kind of sufficient. But for this kind of new constellation with hundreds of thousands of satellites, if you use that strategy, you need many satellites, spare satellites per orbital plane, and that will end up being a huge number of satellites, and that's probably not a favorable way, or not optimal way at least. So we instead consider a different strategy, leveraging again the terrestrial way of thinking of inventory management. So we have this model on the left, which is multi-echelon inventory management, where you have some manufacturer, you have some warehouse, you have some retailer, and each stage have some storage, but each the logistics, the transportation opportunity between each, for example, the warehouse and a retailer is limited. And so here the manufacturer corresponds to the ground, and the warehouse corresponds to a parking orbit that we can optimize at a lower, for example, altitude than the actual constellation. And then the actual retailer is actual constellation planes. And this parking orbit can be optimized, the number of parking orbit, where they are, everything can be optimized in a very efficient way. And also the transportation time between the parking orbit and the constellation plane actually is time varying, because if the altitude is different, the J2 effect is different. J2 basically is Earth perturbation, because Earth is not a perfect sphere. So that is a perturbation called J2, and J2 will cause a drift of the orbital planes, and that drift will be different depending on the orbital altitude. We leverage that feature to design the optimal way to allocate those parking orbits and allocate the strategy to transport the spares from the parking orbit to the constellation plane, so that it's significantly more efficient than having spares in the orbital plane. And we are leveraging some of the natural perturbation, and it's optimized in a very efficient way, because it's a multi-echelon inventory model, is fully analytical. So it can be optimized very efficiently. So again, I don't have time to get into very detail here, but if you have any, if you're interested in this topic, I'm happy to share this paper. I think this is a very interesting way to leverage, again, the terrestrial logistics to tackle some of the challenges of the real challenges in the space development, in this case, spare strategy for mega constellation. Another idea I wanted to talk about is mega constellation deployment, especially here we're using the regional coverage. So this work, by the way, was funded by Mitsubishi Electric Corporation in Japan. If you think about Japan, which is I think same for Taiwan, it's a relatively small area. So if you want to cover Japan, for example, it doesn't really make sense to develop a global constellation like what, for example, OneWeb or SpaceX would do. So there are certain areas of interest like Japan or Taiwan, which is highly concentrated and have a lot of demand, significantly higher demand than other areas, for example, over Pacific Ocean. So does it really make sense if our goal is to save the cost as much as possible? Does it really make sense to have a global constellation, or does it make sense to have a regional coverage constellation? So the idea of regional constellation is not new, but in many cases we may want to expand that region of service over time, and that scenario can be uncertain. So initially you start with Japan. Maybe next you want to cover the US or Europe or India. It depends on the scenario. And then next you want to cover maybe one of the or Europe or India, or after that you cover the rest. And eventually you want to reach a global, for example, constellation. So that can be one way of deploying a mega constellation, because mega constellation over the entire globe in stages can be very time consuming. Like launching hundreds of thousands of satellites takes a long time, and SpaceX has a lot of launchers, but it still takes a long time. if you start to cover the entire globe, then initially you can provide a lot of services. Instead, what this is proposing is to start with a regional constellation to cover this high profitable area so that you can start to generate profit while you're deploying that mega scale constellation. So that is kind of the idea that we developed here. And if we go a step further, even say the coverage over Japan, we may not have the same coverage during the, for example, daytime and nighttime. For example, if you have a communication satellite, maybe there's a larger demand during the daytime and smaller demand during the nighttime. So that can optimize the constellation design even further. So we developed a new way to optimize the constellation for spatial and time dependent demand. So the demands can change over time over different areas, but our optimizer can optimize the constellation. Optimize here meaning with a minimum number of satellites, and you can find some constellation pattern that was not possible to find using traditional conventional constellation design method. So this can be another solution for future constellation design. So I think I only have a few more minutes left, so I'll just conclude here. So basically, I introduced several research areas that are related to space logistics modeling and optimization. And this is very important area, and I want to stress that it is becoming more and more important, more and more impactful, because the space systems is becoming more and more complex. And this growing complexity is where the new research demands will emerge, and we're excited to push forward the frontier of this research area. Thank you very much for your attention.
Yeah, thank you so much, Professor Ho, for this very, very interesting talk, and then telling us many new things. I suppose what you are doing is still very new, right? Supposedly.
Yes, it's getting more and more attention. For example, compared with when I was a student, there's a very different level of kind of enthusiasm in the industry in these areas. So, so I'm glad to see this growing interest.
So I'm asking the audience, whoever has questions, please raise your hands or yeah, and then ask questions. I think that this is something very new, and we need some time to digest. And in fact, for me at least, I want to return and listen to the video a couple of times before I understand fully what that is. But you have a very important point, making important point. That is even for Japan, one has to consider very carefully how to run a constellation, right? Because the country is small. It's not like America, or not like Australia, and the situation would be even moving to the other extreme for Taiwan. And so what kind of? I mean, because we can talk about that in future. This is one of the topics we would like to pursue with you and with SMART. But now here you might just say, give us a quick answer. There is so do you think of any way, any easy way out? That for Taiwan to develop, say CubeSat or small sets, but in the sense that they, of course, we always think about communication, but then here we also think about like Earth observations. Yes. But even for Earth observations, Taiwan is still very small. I mean, then in my mind, I always think that you talk about regional constellation. That means that in my mind, it means that it's not just a single country, but rather a number of neighboring countries, add together, coordinate, so that making the investment more effective, and the scientific return more optimized because of interaction with each other. And do you think this is possible?
Yes, I think that's a very interesting point, and we want to carefully think about how to design a constellation and how to manage that across different players. And like you said, there are certain regions that can strategically work together because of their location, and but then there are of course other situations to consider, the relationship between the countries and whether that makes sense as an investment or not. one solution, one traditional solution for regional satellite is basically having a satellite in the geosynchronous orbit. So I think Taiwan is close to the equator, compared with Japan at least. So it's the geosynchronous satellite can cover the area, but of course it's very far away and it doesn't provide the needed resolution, maybe, especially with a small satellite. Then so there are of course different challenges, so different trade-off we need to perform. But like you said, coordinating with different countries and the design constellation together definitely is a good way to think about, I think.
Yeah, of course we can have say that we have a project in which each country, if you're interested, you could do either in parallel or semi-independent, but put together is a constellation.
Yes.
Of course, that would be a nightmare for your logistic optimization.
So, yeah, one of the research paper that I didn't introduce today was to look into commercialization of space to see. So that was in the context of resource utilization, but I think the similar context applies here too. To look at the game theoretic perspective, to see each player is independent. They want to maximize their utility. Now, what is a good way to interact, and what is a good way to incentivize, those players to work together? So I think that definitely becomes relevant to the problem you're discussing as well.
Yeah, I mean, being a small country like Taiwan, we have a very small space program, but we want to do something interesting and meaningful. So we also need to cooperate with large partner. But the large partner will say that, hey, come on, you don't really contribute that much, So we are always on the sideline. I hope that they're working with you with the Georgia Tech would help to change the situation a little bit. That we learn something that we are able to contribute more, right? I mean, unique. Yeah. Maybe we send a number of students to you to learn this thing. Okay. Yeah.
We look forward to further collaboration. Yes.
I remember that Grant said that you will be responsible for interaction with us, right? Cooperation with us.
Yes.
So that would not be a nightmare.
Yeah, I'm happy to be the point of contact and promote further collaboration.
Okay, good. I think that we have passed the time. It's an hour, and then I think you have done much, and you should do. It's a very, 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 very very informative talk. I would say that, and give us a very complete, new horizons. And I think that we'll go back and next time, I hope that hopefully is that the next time in future, in coming year, the COVID-19 situation is relaxed, and we would like to have a meeting or something in Taiwan, and you should be the first one to come.
Yeah, that would be fantastic. Thank you very much.
Yeah. So thank you so much, and enjoy the rest of the day in Rome.
Yeah, thank you very much for invitation. Again, thank you for your flexibility to accommodate this time change.
Yeah, no problem.
Yeah, we have I have the papers for different topics I talked about. So if any of you are interested, feel free to send me an email.
I'm interested. I mean, there are many papers, but there's one thing I note down is that one by Li et al. In 2020. Li et al. Li H. Et al.
Yes.
You are the last offer.
Yes.
Would it be possible if you send it to me? Yeah.
Yes, I will. I will definitely.
Okay, thank you.
Yeah, thank you very much.
Bye-bye.